We're going to be discussing waves in this chapter. To start off, I want you to picture a wave in your head. What does it look like? Actually do it. Picture some type of wave. I'd be interested to know what it is you imagined in your head. Was it something like this? Maybe you're a sports fan and so you imagine something like this. There's lots of different types of waves, and so there's many different images you could have had in your head. And going over all the possibilities really isn't important. We want to get to the core or the basics of waves. So let's start by addressing this question: what is the source of all waves? Turns out that all waves do share common characteristics, even though there's different types of waves. And the source of all waves is one of those common characteristics. So to figure this out, the easiest thing to do is just create our own wave. If we were in class, I'd just simply bring a rope and we could just start shaking it, and you can see waves travel down the rope. Well, that loses some of the appeal on video, so I'll do what might be the next best thing. Here I have a simulation of a rope. It looks a little funny, but just think of each one of these little circles as individual particles or molecules that make up the rope, and they're all bonded together. This simulation is made by PhET, P-H-E-T. They actually make many useful scientific simulations, and the best part is they're all free. They're all available online. So for this simulation, if we imagine this is a rope and they have a wrench here for some reason just to allow me to hold on to one end, we can create a wave simply by shaking this up and down. You can see how the wave propagates to the right there. Okay, the faster I shake it, the faster the rope wiggles or shakes around. And so really we've answered our question right here, whether you've realized that or not. To create a wave, I need some sort of oscillation or some sort of repetitive motion. And it turns out that that's actually the answer to our question. We wanted to know what is the source of all waves. The simulation showed that in order to create a wave on our string, we needed some sort of repetitive motion, and that's really the key to this question. There's many different ways we could describe repetitive motion. Our book uses the term vibrations. So it says that vibrations are the source of all waves, and that works good enough. Really the main concept is that you need something repetitive. What I want to focus on for this section is something called a traveling wave. Now there's several vocabulary words I need to introduce throughout this video. The first is going to be this term, traveling wave. So what is a traveling wave? Well, I've already shown you an example of it. The wave on a string is a good example of a traveling wave. So here if we have a string and we just start shaking one end, you can see that something is traveling in the sense that it's moving clearly to the right with a well-defined speed. So this is an example of a traveling wave. It's actually moving in some direction. Another vocabulary word I need to bring up is medium. And that's the physical material through which a wave travels. The medium for this example is the rope. The actual rope itself is the material that the wave is traveling through. So if we have a traveling wave, that brings up a new question. What is actually traveling in a traveling wave? Here I have the same idea. It's a wave on a string, but just a slightly different animation. In this one, I want to look more like the PhET simulation where we're looking at individual particles that make up the rope. You can see what the travel here, if I track the high point of the wave, it's clearly moving to the right, so there's a definite speed there. But if we look at an individual particle, that's just going up, down, So in terms of the overall motion of that particle, it's not going anywhere. The net motion is 0. So we can't say that it's the particle or the medium that's traveling, because the medium's still there. The rope actually hasn't gone anywhere. If I stop shaking this, the rope's still there. So clearly the medium is not what is traveling in a traveling wave. Well, maybe it's just the rope. Let's look at a different type of wave. Think of this as the surface of a large body of water, like the ocean. So this would be a surface water wave. Okay, we do have a traveling wave. Clearly, if you track one of these peaks, it's moving to the right, so it enters and then leaves. So something is clearly traveling. Here we're looking at all these dots as if they're the individual water molecules. Okay, so if we track these two specifically, these two yellow ones, they are moving, yes, they're going up, down, and left, right, so they're moving all around, but the net motion is 0. They're not actually going anywhere. The water molecule is still in that general area. So clearly the water molecules are not traveling, which again ties back to our original statement. The medium itself is not what travels in a traveling wave. So to answer this question, we need to kind of think outside the box in terms of something physical. What actually travels is energy. I get that that's an abstract concept, and it's hard to visualize, well, what does it mean for energy to be traveling, but that's really how it works. So what we can say then is that it is energy that is actually traveling from the source that created the wave to whatever final destination that wave has. We've now identified the source of all the waves, so vibration or some sort of repetitive motion. We've identified what is traveling in a traveling wave. It's energy. In this next slide, it's going to look like I'm totally shifting gears, but I'm actually not. Just hang with me. It'll all tie together in just a minute. Here I'm showing 5 different objects. They all have different types of motion, but there's at least one thing they all have in common. Give yourself a few seconds and try to pick out what that could be. What do these have in common? What I was trying to show is that their motions are always repeating. So if you watch all of these, they have different types of motion, but it's all repetitive. It just keeps repeating over and over again. When we discuss repetitive motion, there's several different words that can be used to imply repetitive motion. So I need to make sure and introduce those because I'll use them from time to time. So one way to say repetitive motion is periodic motion. Periodic comes from the word period, which we'll discuss here in a minute. Another way to say it is cyclical. Cyclical comes from the word cycle. Yet another is oscillatory, which comes from oscillation. We could say vibrational, which it's obvious where that comes from. And finally, harmonic. Okay, harmonic motion is repetitive motion or oscillatory motion. All these words essentially say the same thing. In fact, I'll use them interchangeably throughout this video. There's probably more that I haven't included here. I want to look at the motion of one of those objects. Here I just have a mass that's hanging on a spring and it's just bouncing up and down, up and down. To the right here is a plot of the vertical displacement or the vertical position as a function of time. So the reason why the dot here is jumping up and down is because it's matching the motion of the mass. The reason why it's moving to the right is because time is always advancing. So if you combine the position and the time, then it creates a shape like this. I'm sorry the quality's not great here. But the point I'm trying to show is that this position here maps out a nice curve with respect to time. If we look at one of those other objects here, same idea, it's just a mass on a spring, but now it's moving horizontal. If you map out position versus time, you again get a nice wave-like form to the plot or the curve. One last example. This is just plotting the vertical position as this bar spins around. Okay, the vertical position just going up and down, up and down. I like this version because it's showing the evolution of the graph with respect to time. And you can see that the graph evolves much like a wave. It looks and behaves like a wave. It's not actually a wave. This is position and time, but it looks like a wave. Well, mathematically, all of these curves, all of these waveforms share a common trait that they can be described with sine functions and cosine functions. So hopefully you remember some trigonometry from earlier math courses. That's where this would come in. So mathematically, if we wanted to find waves, we would use trigonometry, specifically sines and cosines. In this class, I had mentioned several times that we're not really going to go into the math, so don't worry too much if you don't remember how to use sines and cosines. We won't be using them. But I think it's important that you at least know where the mathematics would take us if we were going to do that. I also want to mention that anytime you have a waveform that looks nice and smooth like this, those are called sinusoidal. And that's not restricted to just sine functions. Anything that can be described with these two terms is called sinusoidal. So if you hear that word, now you know where that's coming from. Now, what I really want to get to is a description of common wave characteristics. So I think we're there that I can start introducing those. All waves share some basic common characteristics. The first two we're going to look at are wavelength and amplitude. So if we assume this orange curve here is an actual wave, so the horizontal axis here is representing a position or a distance, not a time. So this is like an actual picture of a wave. Okay, you think of a wave on a string, if that helps. If you measure the distance between any two repetitive points, so let's just take the peak to peak over there, that's what we call the wavelength. So that's a measurement of distance. In terms of standard units, it would be meters. It doesn't have to be peak to peak, it's really just any two repetitive points. So you could take any random point, you just have to make sure to go where the wave repeats itself. So the wavelength wouldn't be from here to there, because at the start here you're moving up, right there you're moving down, so that's not a repetitive point. So you'd have to move over to where the motion completely repeats itself or resets itself. Those two distances would be equal. The other distance I want to talk about is amplitude. So there's a nice symmetry to our wave. So if you cut this wave in half, this would be our midpoint, this green dashed line. The amplitude is measured from the midpoint to the highest point on the wave, so the point we call maximum displacement. Now it turns out that you don't have to go up, it could also be the lowest point. Really the key is just the maximum distance away from the midpoint. So this right here would be the same measurement for amplitude that this would give us. Let's look at a picture of some real waves. These are surface water waves. Amplitude is usually fairly obvious. It's just, you can think of it as just the height of the wave. You know, you can get a good idea just looking at this for the various amplitudes. Wavelength is a little more confusing. It's not this distance here. That's not the wavelength. It would be the distance between two wave crests. You can see that on the actual ocean, that's not always so easy to identify. There's a lot of variation and variety here. It's because there's a lot happening on the surface of the ocean to give this chaotic nature. So this really isn't the best one to look at to discuss these common characteristics. This is a little better. Think of this as a still surface on a small pond, and somebody just kind of gently tossed a rock into it. When that rock went in, it created these waves that started emanating out from that central location. If we were to take this wave and take a slice of it right there, and then look at it sideways, it would look something like this. Okay, you can see that the surface has that nice sinusoidal waveform. So if we cut that in half, we can identify our two characteristics. Wavelengths, usually fairly easy. You can just take any two repetitive points. In this case, I'm using the troughs. Just remember that wavelength is the distance between any successive identical parts. So we could equally just take any two random points as long as we make sure that they're identical in the wave pattern. Okay, we also would have our amplitude as the distance from the midpoint down to any location of maximum displacement, down or up. Okay, so these are two common terms that we need to know for discussing waves. There's two more that I need to go over. The first one is period. In general, the period refers to time to complete one cycle. So this works for any type of repetitive motion, not just for waves. For waves specifically, though, we would say that the period would be the time it takes for the wave to travel one wavelength. That's when the motion of the wave starts to reset itself. The other term is frequency. In general, frequency can be defined as the number of cycles per unit time. Another useful way to think about it is just how frequently a vibration occurs. So if you have a lot of vibration happening very rapidly, then you would have a high frequency. Of course, if your vibration is happening really fast, then the time to complete one cycle should be really low. That emphasizes a connection between period and frequency. They are inversely related. In fact, you can define frequency as just 1 divided by the period. So this is what I mean by an inverse relationship. If you have a long period, because it's in the denominator, you have a short frequency. If you have a short period, so a small number, because it's in the denominator, that results in a large frequency, so inverse relation. Of course, mathematically, we could just do some algebra there and define period in terms of the frequency. So let's do a practice example. What is the period of a 40 Hertz oscillation? Well, I need to introduce this Hz here. I use the word Hertz. That's what Hz stands for. It's just a unit that's common for frequency. 1 Hertz is equal to 1 divided by a second, or more commonly, inverse seconds. So 1 Hertz is 1 inverse second. Period is just 1 divided by the frequency, and 40 Hertz is the frequency. So to find the period, we just plug it into our equation. A calculator tells me that the answer is 0.025 seconds. So seconds is what I get when I divide by a hertz, or inverse seconds. Okay, so that's unit of time, which I would expect because period represents time. Remember that frequency can be defined as just 1 over the period. So if I take my period value here and just plug it into that relation, 1 divided by that value, I get back my original 40 Hertz. So they just interchange with each other inversely. Period and frequency are concepts that are used in all types of oscillatory motion. they're also key characteristics for understanding waves. There's a couple more primary characteristics for addressing waves that we need to discuss, but let's save those for now. Let's take a little break here. In our next video, we'll cover concepts like wavelength and amplitude, and I'll describe the different types of mechanics of waves.